in the last video I did, I chose not to talk about this periodic table and how to read it. It has a lot of extra information on it. It's a really great version. I wanted to be able to spend a little bit more time with it. Having said that, I have created my own version, which I'll jump over here to in a moment. My own version moved the location of a few things and updated a few things, but overall is the same. So I recommend getting yours out and following along because it might be hard to see here on the screen. Anyway, this periodic table has all of your basics. For example, you have atomic symbols, names, atomic numbers, which remember tells you the number of protons in the nucleus. And as long as it's a neutral atom and not a charged ion, that would also be the number of electrons. Also gives you the atomic mass. He goes out to 1, 2, or 3 decimal places. I tried to be more consistent with the masses that I gave you on my version that I'll flip over to here in just a moment. Furthermore, it has the numbering systems that have been used. The current one, the new notation as he calls it, is the current IUPAC version, is just numbering the columns 1, 2, 3, 4 on up to 18. The older versions are based off of Mendeleev's original table, which only had 8 columns, and when they separated some of the information into those columns basically into 2 columns, they named some of them 1A and the other one 1B, and there were different versions of how to do that, which is where these other numbers come from. Unfortunately, your textbook uses, I believe, the previous IUPAC version. It may even use the CAS version, but it uses one of the old Roman numeral systems. So they're all there so that there's no confusion there. And that information is all pretty standard on a periodic table. Another thing that he put on here is he went ahead and labeled the charges of monatomic ions, and that's these charges that you see up above the periodic table, +1, +2, and so on and so forth. And he even put charges on some of the transition metals that have only one consistent charge. That's one big change I made to mine. I have the charges on all of these transition metals. He simply has a note, if it's shaded in gray, you have to use a Roman numeral for charge. We'll get to that here in a moment. So that's useful information, but again, not too rare on a periodic table. Where his table starts to be different is, one, he has the diatomic molecules listed on here. All the ones that when they exist in nature, they exist bonded to themselves. For example, nitrogen that you're breathing in right now from the atmosphere doesn't exist as just in, it's always bonded to itself, and you have it in 2 molecule. Oxygen, what you're breathing in from the air that you need, is not just O, but instead O2. Now, that's not to say that oxygen is always O2. Of course, you know that oxygen comes in the form of bonded to hydrogens in the form of water, and there the oxygen is bonded to something else, and so then it doesn't have to have a 2. It only has to have a 2 if it is alone. When it's bonded to something else, it may or may not. You'll notice hydrogen in this case does have a 2, but that's just a coincidence, not a necessity. Furthermore, in addition to listing the diatomics, he lists 3 of the other oddities: phosphorus and sulfur. The other one is arsenic, I believe. Phosphorus always exists as P4. This is its most common version as P4. Sulfur, its most common version is S8. And arsenic, I believe, is also AS4. I added that one onto my periodic table. But the real cool thing on this periodic table, and there is some other information like the colors for states of matter and such, are these green boxes and the polyatomic ions here. So there are these things called polyatomic ions. They are ions or things with a charge that are made up of more than one atom or a group of atoms. And unfortunately, there's a decently long list of them. And in the past, it's always been just memorize them. I know when I was in high school, I was supposed to have memorized them. I did not do a very good job of that, and my grades reflected that. It took me a long while to learn my polyatomic ions. It was almost into the school year, to be honest, when we were covering acids and bases that I finally figured it out. What Ed Esquardo, though, who made this table, figured out, he's a teacher down in Cincinnati, and I heard him give a talk on this one a few years ago, is that there's a pattern to the polyatomic ions. He was told to memorize them in college. He sat down with a list of, I think he said it was almost 100 polyatomic ions to memorize, and he wrote them out in the form of the periodic table, and he noticed some patterns. And so he looked at it, and he came up with this pattern now that he teaches, which really saves you from having to do a lot of memorizing. The major exception, outside of the exceptions he has listed in this box up top here, is nitrogen. So nitrogen is an exception. Everything else in the nitrogen column, though, is okay. So you do kind of have to remember that nitrogen is an exception and remember it, but beyond that, you're all right. So what is this pattern? It's a little hard to read, but down here is the 33443 row, and that 33443 tells you how many oxygens are in the 8 version of the ion. We'll get to the different versions of the ions here in a moment. But that tells you how many oxygens are in the 8 versions. So most polyatomic ions are what are called oxyanions. Oxy meaning that they are bonded to oxygen. And so, for example, phosphate is a phosphorus bonded to some oxygens. And we don't know how many oxygens till we come to the bottom of the column and use this pattern 33443. The 4 there with under phosphate means that it has 4 oxygens. The pattern numbers underneath that 33443 row is 32321, and this is the charge. And it's a negative charge, it turns out. And so in this case, it's the 3 here. Phosphate has a 3 minus charge. When I was in school, I had to memorize that phosphate was PO4 with a 3 minus charge. You now have this pattern. You don't have to memorize phosphate. It has a PO4 3 minus charge. You can instead use 33443 and 32321 to figure out that phosphorus is bonded to 4 oxygens and 3 has a 3 minus charge. Now there are several other ions though, not just the ones that end in 8. And for that, you need the box that he has down here, and there I've added a bit to his box. So at this point, I'm going to jump over and show you my version of the periodic table. You'll notice my list of exceptions is a little bit bigger than his. I put nitrate at the beginning and highlighted it so that you would remember, hey, nitrogen's an exception. There's another pattern that I learned that I'll show you when we get to the exceptions. That's what's highlighted in light blue here. And then I moved his chart that he had down in the bottom left corner up to above the middle block of the periodic table. And so I have those there. But this block tells you how to deal with the non-8 ions. And I also have how to deal with a couple other exceptions that he kind of overlooked and such. A couple other changes I made compared to his before I go over those. One, as I said, I have the charges of all the transition metals. There are a few that are missing on this version. I have a more updated version at home that I'm still working on formatting a little bit, and we'll have ready for you when school starts. Furthermore, I've put in italics all of the man-made elements and put in orange all of the radioactive elements, and in addition to the red for gases and blue for liquids. The downside is radon is both, and so radon has 2 colors. And then oxygen can exist as ozone O3, so I went ahead and put ozone on the list as well. But I'm going to jump over here to the notebook where I have the chart already listed. Again, this will probably be a little hard to see, but we'll go with the other ions now. So I chose here on this one to use sulfur as an example. So sulfur, and I don't have sulfur written down right now actually, so sulfur symbol is S. one rule that you'll learn, and one rule that I have here on my chart, is that monatomic ions for metals are named just such and such ion. So sodium, for example, would be this, its ion with the 1+ charge is just sodium ion. However, for nonmetals, they get named I, and so sulfur becomes sulfide, and sulfide is S with a 2- charge. And so the big point there is that sulfur and sulfide are different. One is an atom, and the other one is an ion that has a charge. Then we have the patterns. All the rest of these are polyatomic ions, and they're oxypolyatomic ions, which means they're bonded to oxygen. So sulfate is going to be a sulfur bonded to an oxygen. And we go back here to the chart. S is here, which means it's got 4 on the 33443 and 2- for the charge on the 33443. So it's got 4 oxygens and 2-. There's sulfate. Sulfite, on the other hand, if you come here to this chart, it tells you that 8s use 33443, and ites you subtract 1 oxygen. So sulfite becomes SO, 4 minus 1 becomes 3, and the charge stays the same, 2-. Persulfate is going to be SO, and we add 1 oxygen to the 8. So 4 plus 1 is 5, and the charge stays the same. Persulfate is SO5, 2- charge. The next one is hypoite, and hypoite, I think I may have chosen the wrong color there. There we go, hypoite. We subtract 2, again, from the original, or 1 more from the ite version. So 2 from the original, SO4 becomes SO2 with a 2- charge. And so rather than memorizing all of these polyatomic ion formulas or some general patterns, we have a much more simple pattern to memorize or use to then come up with all these polyatomic ions. Turns out there are a couple other prefixes that we can use for polyatomic ions. There's bisulfate, and so again, it's going to be a sulfur bonded to some oxygens. The 8 here means that we are still looking at the 33443, so it's going to be the same as the sulfate was over here. Sulfate had a 4, so it's going to be a 4. And what you see on the chart that bi does is that we add a hydrogen before the formula, and we add +1 to the charge. We add a hydrogen here. The original charge was 2-, add 1 to that, and it's now 1-, so this has a 1- charge. There's also thio as a prefix, and by coincidence, thio deals with sulfurs. You'll notice on the periodic table that sulfur and oxygen are in the same column, so sometimes instead of being oxyanions, they become sulfoanions, or thioanions, or what we really call them. And so sulfur replaces one of the oxygens you'll see. And so we go from SO4 to now having 2 S's and O3 instead, and the charge stays the same, 2-. Theoretically, you could have maybe thiosulfite. And thiosulfite, we'd then follow the same rules. We'd take sulfate, and we would take away one of the O's, and the charge would stay the same. I don't even know if that one actually exists, but theoretically we could figure out its formula from something like that. And that's the basic pattern to using this chart to figure out the formula of a polyatomic ion. Those polyatomic ions will then form compounds and such, but there you go. I do want to talk about the exception nitrate. Nitrate, according to this chart, should be NO3 with a 4 minus charge, but nitrate in reality, as you see up here, is NO3. Excuse me. Nitrate should be NO4 with a 3 minus charge, when in reality it's NO3 with a 1 minus charge. This one's the only exception of all of these, and because of that, then you just have to remember nitrates. It's one that you kind of have to memorize. But from there, nitrate follows the normal rules. So nitrite, so this is nitrate, nitrite, take away one out. And hypoite, so hyponitrite would be NO with a 1 minus charge, although I don't think that one actually exists. So on and so forth. So that's the examples there, and I recommend, as practice, that you try doing the one I showed on the previous periodic table. Try going through all of these prefixes and suffixes with phosphorus, nitrogen, and carbon. And that should give you a pretty good feel as to whether you have the hang of this. The other thing is there is a decent list of exceptions that you have to memorize. You just kind of have to know them. Within that list of exceptions, there is a shortcut, though, for figuring out the charge. However, I should point out that there are exceptions to that pattern. Pyrophosphate, which I highlighted, is one of them, and all the positively charged ones, mercury 1 and ammonium, are also exceptions. So those do not follow this pattern highlighted in cyan, but to determine the charge of the ion, you add the group numbers. If it's even, then the charge is -2, and if it's odd, then the charge is -1. So for example, if we take cyanate, carbon, its group number is 14, nitrogen, the group number is 15, and oxygen, the group number is 16. So we add those together, and we're going to get 45. 45 is odd, so the charge is 1 minus, and you'll see that cyanate's charge is 1 minus. Cyanide, right next to it, we take away the oxygen, and you should be able to see that that's still an odd number, and so then its charge is also going to be 1 minus. If we instead find maybe one of the evenly charged ones, here we go, chromate. Chromate has a charge of, we can figure out its charge for chromium is in group 6, and there are 4 oxygens in group 16. So 16 times 4 is 64. And then add 6 to that, and we get 70, and you can see that 70 is an even number, and so chromate's charge must be 2 minus. It works. It's a pattern that I've picked up since Anna Squardo showed me this periodic table, and I thought it was incredibly useful. The one other thing I want to point out on this periodic table, he had on his the Greek numeric system, and I unfortunately had to flip mine sideways to make it fit on the chart even, but I had the Greek and Roman numeral system as well, of course, our normal Arabic numbering system, and if you didn't know, our numbering system actually comes from the Arabs. And furthermore, they were one of the first people groups, although there's evidence that maybe the Indians had it as well, the Asian Indians had the concept of 0 as well, that no other culture had really that idea before. But anyway, we use the Greek numbering system only with molecules that are called hydrates. and we'll get into how to name those later on. And then the Roman numerals, I think we only go up as high as 7 or 8, but I went ahead and put all the way up to 10 just in case, and because there's room for it. But with all of these transition metal ions, for example, copper here can be a 1+ or a 2+. And so we have to have something in our naming system to say, is this copper with a 1+ charge or copper with a 2+ charge? And what we decided is to use Roman numerals. So copper with a 1+ charge is called copper 1. It's that convenient. And copper with a 2+ charge is called copper 2. I probably should have color-coded those, but there you go. And the exceptions to that naming system are the ones here that are highlighted in yellow, or excuse me, in white, or are not shaded in behind them. Those do not need Roman numerals for their charges. I think gallium does. I'll have to look up that one for sure. And aluminum, I know, does not as well need a Roman numeral. For all these others, they need a Roman numeral. And on the full version of this, I have charges there. Now you'll notice on something like zinc, zirconium, I have only zirconium 4+. That's the most common one. It can form others. But if we ever use zirconium, odds are you're going to be using zirconium 4+. And so then I didn't bog you down with all the other unnecessary charges. But that's all the extra information on this table. I recommend trying those practices like I suggested. And we'll review this just briefly this school year, but really naming compounds and knowing your polyatomic ions is something you just have to have right off the bat.